We are selected as the project team at Omicron Theta Cybernetics Private Limited develops memory chips of standard weight at 3.560 grams each for the Man-to-Mars space mission. Our group need to evaluate the output 2 working shifts data of morning and afternoon for a 5-day weekly shifts by using quality control tools for histograms, check sheet and control charts. Also, make us suggestions to improve the quality. Check sheet. Check sheet is a simple document that is used for collecting data in real time and at the location where the data is generated. The document is typically a blank form that is designed for the quick, easy, and efficient recording of the desired information, which can be either quantitative or qualitative. The check sheet is one of the 7 basic tools of quality control made popular by Dr. Kaoru Ishikawa. A defining characteristic of a check sheet is that data is recorded by making marks or checks on it. A typical check sheet is divided into regions, and marks made in different regions have different significance. Data is read by observing the location and number of marks on the sheet. There are 5 basic types of check sheet. These types are classification check sheet, defect location check sheet, frequency check sheet, measurement scale check sheet, and checklist. Histogram. Considered as one of the basic tools of quality, a histogram is a graphical representation that organizes a group of data points into user-specified ranges. It was first introduced by Carl Pearson. Similar in appearance to a bar graph, histogram is used to plot the frequency of score occurrences in a continuous data set that has been divided into classes, called bins. However, the difference between histogram and bar chart is that histogram is used for continuous data, where the bins represent ranges of data, while a bar chart is a plot of categorical variables. There are 6 major patterns in histograms that can be described as skewed left, unimodal, symmetric, skewed right, bimodal, multimodal, and symmetric.
Control charts, also known as Shewhart charts or process behavior charts, are a statistical process control tool used to determine if a manufacturing or business process is in a state of control. The control chart was invented by Walter A. Shewhart, who worked for Bell Labs in the 1920s. The company's engineers had been seeking to improve the reliability of their telephone transmission systems. Since amplifiers and other equipment had to be buried underground, there was a strong need to reduce the frequency of failures and repairs. By 1920, the engineers had discovered the importance of reducing variation in a manufacturing process. They also realized that continual process adjustment in reaction to nonconformance increased variation and degraded quality. Shewhart framed the problem in terms of common and special causes of variation, and on May 16, 1924, wrote an internal memo introducing the control chart as a tool for distinguishing between the two. Shewhart's boss, George Edwards, recalled, "Dr. Shewhart prepared a little memorandum only about a page in length. About a third of that page was given over to a simple diagram which we would all recognize today as a schematic control chart. This diagram and the short text have set forth all the essential principles and considerations, which are involved in what we know today as process quality control." Control chart is used to analyze the changes of a process over time, where data are plotted in time order. A control chart always has a central line for the average, an upper line for the upper control limit and a lower line for the lower control limit. These lines are determined from historical data. Control charts for variable data are used in pairs. The top chart monitors the average or the centering of the distribution of data from the process. The bottom chart monitors the range or the width of the distribution. By comparing current data to these lines, a conclusion can be drawn about whether the process variation is consistent or is unpredictable. This versatile data collection and analysis tool can be used by a variety of industries such as manufacturing and business and is considered one of the 7 basic quality tools.
Let's continue on the next part, which is the analysis of histogram results. The first step in creating a histogram is collecting and sorting all of the necessary data, which in our case is the weight of memory chips produced from Monday to Friday for both morning and afternoon shift. Since the data is too much, the data of one day for both shift is divided into 5 subgroups. The next step is to create a tally sheet based on the data collected before. Here are the examples of tally sheets for Friday morning shift data, which has been sorted based on the specified weight of memory chips with the interval of 0.05 grams. For the next step, we need to calculate the ranges, cell intervals, cell midpoints, and cell boundaries. Here are the formulas to calculate all of the variables that are used to construct the histogram, where the specified cell interval indicated as small capital I is set to be 0.1 grams. For the last step, we plot the histogram using all of the calculated values mentioned in the previous step. Here are the examples of histograms for the Friday shift. From both histograms, it is observed that the histograms produced random distribution. Random distribution means that the histogram lacks an apparent pattern and has several peaks. Overall, both histograms show that the memory chips made on Friday are mostly uniform. It indicates that there are fewer variations that occurred during the production of memory chips. Even though the production process of memory chips for the Friday shift is relatively stable, it still needs to be tweaked in order to meet the standard quality of 3.56 grams. Hence, histogram helps identify the variations and distribution of the products to achieve the standard quality specified for the products. The details of the histogram for other production days are included within the reports.
Control chart result.
There are 5 steps to find control chart, which is: first step is assumptions and considerations taken for calculation. Second step is collect the data for each subgroup. Third step is calculate the mean x-bar and range r of each subgroup. Fourth step is calculate the centerline and control limits for the control chart. Final step is plot the x-bar chart and r chart based on the information gathered in step 3 and 4. For each control chart, there are 20 subgroups with 10 random sets of data taken for each subgroup, which makes it 200 data samples in total for one shift. It is divided into 2 parts which represent the data samples for morning shift and afternoon shift. This is the formula used during calculating control chart, which is mean x-bar, range r, centerline x double bar, upper control limit UCL, and lower control limit LCL. This is the result for Monday. The mean of memory chips produced in grams for subgroup 17 is out of control limit. Actually, an out of control process indicates the presence of non-random variation. Non-random variation is caused by definite, specific causes that are called assignable causes. These assignable causes make the process go out of control or become statistically unstable. The presence of an out-of-control condition should prompt further investigation. It is important to find the assignable causes and take action to remove them. Once assignable causes are removed and only random variation due to common causes remains, the process will become stable and return to an in-control condition. For Tuesday to Friday, the control charts show the x-bar and r-bar charts in under control and not exceed the UCL and LCL value. Thus, the output of memory chips produced in grams from the factory is in control.